Welcome to class today. We're going to do the chain rule for one variable function. And here I have a nice little diagram on my handwritten paper. All right, very exciting day, chain rule. But before we get there, let's remind ourselves, what's the interpretation of the derivative? Do you remember? And I'm thinking of three interpretations. Can you give me any? Ian, go ahead.
How a function changes over time.
Okay. Specifically, can we be more specific? Go ahead.
The slope of the tangent.
Oh, I like that. Slope of the tangent line. Any others? How about something physical?
Like speed?
Yeah, velocity. Derivative position function, right? Okay. So this is your age-old definition, instantaneous rate of change, where you look at the average rate of change, this difference quotient, and then you take the two, that's interval of time to zero, right? All right. Versus, well, another interpretation is the slope of the tangent line. So here I have some function of x here in violet, and then I'm drawing the tangent line at that point. So the derivative is the slope of the tangent line, right, at that point. And this is the one, the physical system I want to leverage today. Velocity is the derivative of position. So v of t is dx dt if x of t is the position, say, of a car driving. So, do you like my little car? All right.
Very artistic.
All right, so this is the one we're going to leverage. All right, and so let's think about a car driving to the right, and we're going to model the vertical position, and I know I call it x of t, it's for later notation. So we're going to model the vertical position, x of t, as a function of t, and here this car is going to brave this steep slope here. So we're going to have it going to the right, and we're going to model the vertical position, x of t. And I can put some axes on this, okay? And maybe we prescribe the function itself. It's an upside down parabola, 1 minus t squared. And so the vertical position is x of t at any time t. All right, and the velocity then is what? This derivative, dx dt, is just what? The power rule, right? Minus 2t. Great. All right, and we can superimpose that velocity function on there, minus 2t. Right. If I start to climb up that hill, I'll start at the highest velocity there, right? And it'll start to decrease over time. The car gets to the top of the hill. It's going to turn around now and start to have negative velocity, right? All right, finish it up. Great. All right, so let's take that example and let's modify it a little bit. So this is now, instead of like a parabola-shaped bump, let's think about a semicircle bump. And this is pretty hard to get through right here, right? But just go with it. In math, we do some abstractions, right? So we're thinking of the position now, the vertical position. Before we had it as this parabola, x of t equals 1 minus t squared. And let's now think of a semicircle. So if I compose that x of t with the square root function, f of x of t equals the square root of 1 minus t squared, then I can equivalently write it as 1 minus t squared to the 1 half, right? And how are we going to take this derivative? How are we going to find the velocity of the car in the vertical direction? Right. So that's the complication for today. We need a new tool, and that tool is called the chain. So let me write our example up here. So here we're thinking about the car, remember? And x of t was prescribed by 1 minus t squared. And f of x was the square root of x, which I'll write as x to the 1/2, because I'll think about a power rule in a minute. And our question is, how do we get this derivative, d by dt, of the composition of f of x of t? That's our question for today. All right, how to find this derivative. And I'm going to draw a diagram for you, which was like something that a mentor of mine drew for me the first time I was learning like partial derivatives. All right, the chain rule for multivariables, excuse me. So what I'm going to do, I'm going to start in the t variable over here. And to get to x of t, I use the function x. And x of t through f maps me to f of x. That's just the composition of functions. And now we're asking, I want to take a derivative with respect to time of this function, right? So I want to take a derivative and it acts on the outside of this function and I need to get to the t, right? But there's stuff in my way. All right, so in order to get to the t, we first have to differentiate with respect to x, f prime of x, and then we differentiate x prime with respect to t, which I'll denote dx dt here. And the chain rule tells us that the derivative of this thing is the product of these two things. Right? That little dot represents the product. All right, so we can fill in our theory here. This is general. All right, so it says f prime of x of t, f prime evaluated x of t times the derivative dx dt. All right, and this is the chain for one variable functions. All right, so we have our theory. Let's go back to our example. So we have our theory. Well, here's the formal statement of our theory. So the chain rule for single variable function, suppose x is differentiable at t, f is differentiable at x of t, the composition, then the composition f of x of t is differentiable at t, and namely the derivative is the product f prime of xt times dx dt. That's what I wrote there. All right, just giving you the formal statement. All right, and so back to our problem. We're still trying to find the velocity in the vertical direction of this composition of functions, right? And maybe we'll do this on the board now. Okay. So what's the derivative of x with respect to t? Not everyone at once. Negative 2t, good. All right. And let's make sure I do this right. F prime of x, I'm going to use that form and use the power rule. What is it?
1/2 x to the negative of.
Yeah, and I skipped to it. Sorry, let's write what you said. 1 over 2 x to the 1 less power, right? Bring down the power, 1 less power, all right? And I can rewrite that as 1 over 2 times x to the 1/2. Great. We're in good shape. And let's use I think we're ready to compute d by dt of the composition. All right. Great. I wrote that. Now we have to do f prime of x of t. F prime of x of t, right, times dx dt. Again, just writing the formula. F prime of evaluated x of t, 1 over 2. Okay. I'm going to put x of t to the 1/2 here. What was x of t? All right, so I'm going to put 1 minus t squared to the 1/2 power. All right, times what goes here, dx dt. So I'm going to put that down there, minus 2t. Do everything correct so far? Transcription? Okay. All right, my favorite part. It feels so good. All right. And you can put it as a square root if you want. 1 minus t squared. All right. Okay, so we solved our little problem here. We got the velocity in the vertical direction. And we had to use our new tool, the chain rule. And I can superimpose that velocity function in light blue again. Oh, we got our car moving up. Okay, great. Reaches the top. Great. We're going to go back down. Great. All right. So we did it. We're done. No. All right. So we have our tool, the chain rule. And now I'm going to tell you about my favorite application. In quotes. So I'll just tell you, this is what I love about math. I realized in undergrad that I would not be able to go to med school because I don't have the memory for it. So what I love about math is if you remember certain principles, you can always get back to the thing you were supposed to remember. Okay? So we're going to do my favorite application now, and it's because I have a poor memory. Oh, no. All right, so here's my favorite application. Of the chain rule. Not an app on your phone, but an application of the chain rule. Okay, so let's find the derivative of this. Okay, how are we going to do this? All right. Does anyone have any ideas? What do you think? Dakota, you're closer to this.
Yeah, you can take the T out front and then.
I think you have the right idea. So I'm going to take the natural log of both sides. Okay. Oops, I read it a little different. Natural log of both sides. All right, maybe we'll call this f of x. We'll call this f of x of t. So here, f of x equals the natural log of x. Great. What can I use here? Gonna do some algebra. Yeah, I want to do what?
Take the T and put it out front.
Yeah. You have to make that noise too. Okay. All right, and what's this thing? It's just a constant. Great. And we know how to take this derivative, right? And we're going to have to use the chain rule. We know the derivative of this. All right, so what's f prime of x?
1 over x.
Yeah, 1 over x. Excellent. All right. You get the jokes for free. All right. And so we're going to take the derivative of both sides. Remember, we got our chain rule, d by dt. F of x of t equals f prime of x of t times dx dt. All right, so if we take a derivative here, we're going to get, we'll say d by dt, one over x of t times dx dt. That's the thing we want. That's the thing we want. All right, so that's the left-hand side, so I differentiated that. On the other hand, it's a constant times t, so what's it equal?
A constant.
Yeah, just that constant, right? Excellent. And I'll run out of space. What was x of t? Yeah. So now I can go here, put that in, multiply it to the other side, and I'm gonna squeeze it in. The derivative, dx dt, is equal to x of t times ln of a. X of t is a to the t times ln of a. The thing I can't remember. All right, and we see, right, what if a equals the natural number e, right? Ln of e is 1, and we'll just get e to the t. Great. Huh. All right, so we've successfully done my favorite application, and that concludes our inquiry into the chain rule for single variable functions. Okay. Okay.